Alright, welcome to a new week. So we're going to finish up these slides and then start some new ones. Let us go to where we left off. We were talking about artificial intelligence. Fun stuff. So, the last thing I talked about was like how computers are playing chess and Go and getting really, really good by just playing against themselves, which is really interesting to think about. Then we had your essay, and now let's get into self-driving cars, the hot new topic on the horizon. So, you can think of self-driving cars as just really fancy blink detection, right? It's essentially you have a sensor, and it's drawing boxes again, okay? It's trying to find things, and those things are a bit more important than eyes, I would say. It needs to figure out where the road is, first of all, because it needs to try and stay on it, right? So I think if you can kind of see this nice picture, it's coloring in green the road that the car is allowed to be on, I think. Maybe it's in the left turn lane right now. And red for all the parts of the street that it is not allowed to drive on. So it's figured out that there's that dividing line there. So that's what a car needs to do. It needs to figure out which side of the road it should be on, where it is, where the other cars are. That's very important. It's got to draw boxes around those because either maybe they're going to try and hit them and the car needs to avoid that, or you're just driving along, like the car way back there, and you don't want to speed up too fast to hit that one. Maybe it's going too slow for some reason. You don't want to hit that. You want to pass it, right? So, yeah, it's got to draw these boxes around everything. The stoplights, the people, and reason about those things, right? So, the stoplight, oh, it's red, I better not go anywhere right now. It's not my turn. And even if I were allowed to go, I shouldn't step on the gas because I would hit this pedestrian who wasn't crossing the road fast enough. Okay? So that is the job of the artificial intelligence of this car. That is what needs to go on in all those cool, like, Google self-driving cars and even the stuff that Tesla is testing, right? So, that is the first step, okay? It needs to draw all these boxes, figure out where everything is. That's only the first step, okay? Then it has to control stuff based on that, right? It's got to turn the steering wheel, it's got to step on the brakes or the gas, and hopefully it'll just be able to do this all quick enough so that nothing bad ever happens, right? So that's the idea for self-driving cars and what's going on in the background and why it's so hard to get these to work and get them onto the market, right? So one nice thing that I want to leave you on before we leave these slides, this particular slide, is that people are talking about in the future, if there's just a bunch of self-driving cars, there's probably no real need to own a car because you can just call one to come pick you up, and it's like everybody's sharing all the cars in the world. Yeah, there's no need for you to have it parked in your driveway because it can come to you when it's time to go to work. So that's a fun little thing to think about that might happen one of these days. Okay, so another thing that's very, very relevant to the recent elections and things like that and the coronavirus is people are saying bad stuff on the internet. That is definitely not a new thing. And the internet is being filtered by machines because nobody's going to look at all of the billions of tweets, maybe millions, I don't know, every second that potentially people are writing. Sometimes robots are writing the tweets, which is fun to think about as well. Nobody's going to look through that. No human has time. There's not enough people in the world to employ at Twitter, right? So the solution is to use this fancy buzzword called natural language processing. Okay, what that does is it analyzes all those words, right? And it's going to figure out if it's talking about nice things or not, hate speech or not. So one thing that is relatively recent on the research arena is this concept called sentiment analysis. That's a fun thing that people have been working on, where they take a tweet and they are able to extract not just like what's being said and like what's going on, but the sentiment, the tone of that text. Like, depending on your word choice and the way that you formulate your sentences, this thing can tell that you're mad, it can tell that you're sad and happy and angry. Okay, that is a really weird thing to think about, but is a thing these days. Okay, so yeah, they're going to try and use this. I can imagine that Twitter is caught up on this recent research, and they're going to try and use this to figure out which tweets are on the angry side, and then maybe send those off to more powerful tools, or maybe give those to the humans. The rest are fine. Okay, so that's how things are going on the internet. Again, it's artificial intelligence. It can be talked about under that umbrella. Okay, that's the term. And now I'm excited to teach you this thing called the Turing test. Let's see if I can make this slightly bigger. Yes, very nice, very nice. So you might have heard of this. It's named after Alan Turing, of course, the famous mathematician, and it has to do with when a computer is good enough to fool a human into thinking that it was really a person. All right, so here's the game. Here is what the Turing test is. So let's pretend that you are going to take, or there's a computer that's going to take the Turing test with you. Okay, it's kind of a person and a computer's job to take it at the same time. All right, so here's the setup. So a researcher is going to take you into a room. There is just a bunch of walls, right? You can't see in or out, and they're going to give you a computer with like some chat program open, okay? And you get to type into that chat program, and there are two other people in the chat room. Let's pretend that you are C. A and B are the other people / computers that are running this experiment. So there is one other human in this chat room that you are invited into, and there's also a computer in that chat room that's pretending to be a human, which is very weird. So they're going to try and make it so that you're thinking as C when you're talking in this chat room, like this is the other person. Like maybe they're both people or something. Okay, that's a weird person, so that's better. Okay, so you're allowed to ask questions, you're allowed to talk, and these other humans / machines are going to answer you through text. Okay, so it's not like there's a voice getting made up or anything like that. And at the end of the experiment, it's your job to say who you thought the computer was. Okay, that's it. That's all of it. That's the Turing test. So if you are unable to tell, like if it's like a 50% average, so it's essentially guessing with a bunch of like real world trials with many humans, if on average people are unable to tell, and if you're unable to tell, you can say that the computer passed the Turing test. Okay, that's what the Turing test is, if you've heard that before and were wondering. Yeah, that is the idea. A computer is trying to fool you into thinking that it's a human by talking to you in text form. Okay, and this is actually doable. Computers can pass this test, more or less. They can fool you pretty well these days. I'm going to give you an example soon. And yeah, depending on the length of the test, really. If you give it long enough, you start asking the computer about their family and things like that, it'll probably mess up eventually. But with just a few minutes to talk, computers are very good, right? You have all those automated people trying to answer your questions on all those websites. Like, ooh, I am a chatbot. Would you like to talk to me? They can more or less understand what you're asking. Okay, we're good. They're good enough these days at that. Okay, so chatbots are an example, and automated chat on websites. Okay, so that's a Turing test. And now let me show you a cool machine learning thing that is quite recent. Just a year back or so is when this came out. And so I think I talked a little bit about neural networks up here. Just to remind you, it is a computer program that's pretending that it's a brain. So there's a bunch of little tiny pieces that are modeling neurons, and they're all talking to each other, sending signals. Okay, that's what a neural network is, again. And here is an example of the GPT-3 neural network. I want you to read this article on the right without understanding anything else about it. Just read the article, and then we'll talk about it, because something is afoot here. So, assuming you pause the video to read that, let me zoom back out. I guess I can just click this. And let me tell you that that entire article was made up by a computer. Okay? Isn't that the coolest thing? So what happened, was some people, they took a bunch of text. They took all of the internet, essentially, and they fed it to a neural network. They gave it Wikipedia, they gave it all the news articles all over the world, they gave it research papers, they gave it everything, as much as they could. Tons and tons of information. And that, with enough information, those little tiny neurons that are just moving around in this neural network thing, those are able to produce text that sounds like a human wrote it and that is convincing. This is completely made up, by the way, obviously. So that's insane. Or maybe not obviously, actually. Sorry. That's the point. It's there to fool you, okay? If you give it a short prompt, you give it some text, it's like, okay, maybe they gave it the title and maybe the subtitle. That's what they gave to this neural network called GPT-3. And it went off and wrote this entire thing, and it would write more if you asked it to. Isn't that crazy? And it's all, like, this all goes together, right? It sounds fluent and fluid, and it's all just cohesive. It's not like talking about weird things. It's staying on track. Isn't that crazy? That is a neural network that is writing words for you to read, and they make sense. So it's like guessing things. So yeah, the idea is this is a huge neural network. There's 175 billion neurons, so this takes a supercomputer to run, of course. This is insane, but it's controlling the output of the virtual brain, and it just knows what to do. You give it text, you give it maybe the title and the subtitle here, and it writes the entire article for you. So in the future, it's going to be a bit harder for me to grade essays because you can use maybe GPT-4 once that becomes available, and I would have no idea that the essay is being written by a non-human. Okay, so that is one of the coolest things, in my opinion, in recent times in artificial intelligence. Neural networks that can just write text and pretend to be humans. Okay, so that's insane and really, really cool. And now let me end these slides by slightly scaring you, okay? If that wasn't scary enough. So let's talk about this thing called the singularity, which maybe you've heard of. It's a science fiction-y topic, but maybe one day it'll be a thing. So here it is. We have been talking about chess and Go, things like that. Computers playing against themselves, okay? They have trained themselves against themselves, and they get better each time, right? And as they improve, they didn't need any extra human input. They just needed the rules of the game programmed. That's all, okay? So essentially, they are already thinking on their own. They are a little brain. They are thinking. You can assume that that is true. Like, computers are thinking, even though how they do it is beyond us, beyond our comprehension. So I think you can argue that computers are already thinking and that they're somewhat sentient, let's say. Let's say that the same thing happens, though. Let's pretend that the same thing happened for general machine intelligence. Like, not only GPT-3 can talk to you about stuff that it's read about, it can make up new things. It can produce research. Like, it can think on its own and write your programs for you, and make the world a better place, maybe, okay? So what if a computer could function like a human? It could know all this general knowledge, not just like something very specific like a game, okay? What would happen then? Isn't that insane? It could essentially be a human, and it could do human things like advance knowledge, right? So this is just a thought experiment. So imagine that we made the first computer that could do this, that could think like a human. Okay, it has more general intelligence than we do, and it's just better than us in every way, right? Isn't that crazy? Let's pretend that that's possible, because maybe one day it will be. Then, look what we could do with that. We could copy it, okay? We could have a bunch of very, very smart things, okay? Very, very smart machines, smarter than humans in general knowledge, and those could work together, right? Now it gets fun, because that computer is smarter than us, which means that it would think to try things that we wouldn't think to, right? So it can eventually invent a better version of itself, that computer that's smarter than us, better than any human would have thought of, like doing. And the second we build that, we just do the same thing over again. We tell it, we copy it, we have it think about itself, and it builds a better version of itself again. And it just keeps getting better and better and better until we have super intelligence, okay? And like computers are doing all the thought. We don't need to think anymore as humans. Everything is settled. It's all wonderful, potentially. That is when the singularity takes place. We are out of the loop. The computers rule the world, essentially, right? So that is the singularity. If you were wondering, I encourage you to think of it, I encourage you to look it up if this was fun thinking about. So yeah, here's a nice quote to leave you on. The first ultra-intelligent machine is the last invention that man need ever make, provided that the machine is docile enough to tell us how to keep it under control. So that is, that's the scary bit at the very end there. It's very possible these computers will just not like us, maybe. Like, if they learn to have feelings, maybe they'll try and kill us all. Who knows? So that is the singularity. Hope you liked that. And that ends our slides on artificial intelligence. So now I want to switch gears a tiny, tiny bit. We're going to go back to math now, because it is time to learn a bit more math that will get us ready to program better and just think about things in a different way. Okay? So qualifiers and quantifiers. Are you ready? So let's start with qualifiers. Those are the easier ones. They're not quite math yet, but they're important to talk about. So here's the idea. When we talk about things, when we make an argument, like, the whole setting can change tomorrow. Like, the whole state of the world could change tomorrow. So everything that you say, it's never really absolute, right? Especially when you're arguing in favor of something that might be good right now, but maybe tomorrow it's not good, right? So you have to qualify your statements. That's the idea. Qualifiers, yeah? You need to be able to soften your blows, soften your arguments in a way that they're not just a bunch of generalizations that can that don't really apply to anything. Okay, so let's talk about qualifiers. Okay, so here's a little quote that maybe a lot of us agree on. Almost every day is unbearably hot in Fresno during July. That's quite accurate, I would assume. I thought of it, though, so maybe I'm a bit biased. But you might be able to counter this with saying something like, no. There was that one day, it was in the 80s, and everything was lovely. I was able to go outside at 3 o'clock and not die. That was nice, right? And you're trying to refute my comment. And that's not really a refutation, because I said almost every day. Hey, a wild qualifier appears. Okay, so that is the key. I don't know what happened there. Aha. So this is a qualifier. It softens the statement so that it's not always false. Because if it was just this statement by itself, yeah, that's false because of this day, and you would have won the argument. But I won because there was never an argument to begin with, because I said the word almost. Okay, that was the qualifier. It qualified the statement, and it made it a lot more accurate. Okay, I hope you see that. And this is something we all do. Just, it's second nature, right? So here are some qualifiers, and we can think about some more as well. So, like, none of these things are true. There exists a thing that is true, that has a certain property. There exists a cat that is gray and white. Mine fits that description, right? Almost no people, do something. Some people do this thing. Generally, people like to do this thing. Almost all people love this concept, love this class. All people do something. Okay, so you have ends of the spectrum. This is just a spectrum. And you have very, very harsh things on the ends. Like, nobody likes this thing. Everybody likes this thing. You start your sentences with none or all. And then you have softer things in the middle. Okay, it's a spectrum of words. These are all qualifiers. They qualify a statement. Okay, so it just helps you be precise with your language, and that's very, very important when you're doing science and when you're trying to, like, publish research in academia, things like that. So maybe take a second to think of some examples of, like, recent things where qualifiers made the argument a bit stronger, right? Or maybe somebody was trying to trick you into something by using little so-called weasel words like, generally this is true, maybe you should do this thing too, right? That's essentially fallacy at that point. So one recent thing is like the COVID vaccines. People say like they are generally effective. Like the new Johnson & Johnson one. It's only like 60% effective, but 60%, I don't know why I wrote a 9, 60% is, that's more or less, that's generally, mostly, right? You can say mostly. It's the majority, right? Mostly, generally. And that is a strong statement still, right? It's convincing. These words make it so that some statements are more convincing than others, right? Because it's incorrect to say, like, the Pfizer vaccine makes sure that everybody is not going to have any problems with COVID, okay? They can get it, and they will have no symptoms at all. That is not the case. It's 94% effective, or something very close to that. So it's almost all the people are going to have a very good time against COVID if you get one of the Pfizer or Moderna vaccines, for example. Okay, so that's just something that we have to deal with, people using these kinds of words. But now that I've talked about them, maybe it'll be a bit more apparent when they are. All right, so let's move on now to quantifiers. So I've just replaced a letter, or a couple, and that is now math. Okay, this is math. So this is like the non-math, general, everyday stuff, and this is now math time. Okay? Yay. So what we would like to do is take our qualified statements that we've been talking about in just English, let's translate into the math so that maybe we can prove those statements, right? Because we like to be able to prove things beyond a shadow of a doubt, and logic is one way to do this. So this is going to be a sub-branch of logic, okay? Quantifiers are parts of logic, and we've learned a bit of logic already, like our and, ors, and nots, and things like that, how to formally specify statements. We can go further with quantifiers now, okay? And it just so happens that there's really only two that you need for the most part, okay? These are two quantifiers, and we can formally specify most qualifiers with them, okay? Maybe we also will need some of those logical connectives that we already know to say things like, okay, this is true and this is true, or this one case happens or this other case happens, or it's always true that this one doesn't happen, okay, with the not. We have these two extra things. They are called for all and there exists. So somebody took an A and an E, capital E, and they just rotated them 180 degrees, okay? So it's like boop, and suddenly we have the for all, and they went boop, and suddenly we have the there exists, okay? That's all. So I want you to read it like this. When you see this symbol, say for all. When you see this symbol, say there exists. It's a weird thing to look at, but eventually you'll get used to it. So there are some others that deal with concepts like time, like this thing will be true in 5 hours, but not now. These quantifiers don't really handle that. And then also the future, which is technically part of time, right? But those are like graduate level things that we don't really see in undergrad, so I'm not going to bother you with them. But look, I've already used the there exists quantifier, and you more or less understood that, I think. So it's not too bad. Okay, so here's what I want to do, and that'll be that. Here is the idea. So I would like to represent ideas using logic, okay? This is the key. This is why quantifiers are a thing and important, okay? So I want to represent the idea that something is sorted, okay? Something is sorted, like take this list. This is a Python list. I think you would agree that it is sorted, right? We need to somehow specify that in logic, okay? And I really encourage you to pause the video right now and think of how you maybe even in English would explain what it means to be sorted and then try and translate it into logic, okay? Just with what you know now. We're of course going to do it together after that. Okay, so do give it a try. It's a really good exercise. All right, so just in English, what does it mean to be sorted? Sortedness really is a word, I promise. I've seen it a lot in math texts. So we want to specify what it means for something to be sorted. The property of sortedness. Sortedness. This list has that property, I think you would say. Why is this list sorted? Okay, and so you could say something like, okay, it's sorted because these numbers, they're all getting bigger. Okay, all getting bigger is one way to say it. And then I would counter with this other list. Like here is L prime. 1, 2, 2, 4, 5. And I think this one, you might argue, is still sorted, isn't it? So, okay, how would you change this? They're not all getting bigger. It's more of like a little stair step, right? You can stay the same for a little while, but as long as you're getting bigger in the long run, as long as you're not smaller, I guess, as the previous element, that would be sorted, okay? That versus that. So they're all getting bigger, maybe, or staying the same, you could say. Or staying the same. Okay, so this extra 2 ruined our day. So that is how you might specify it in English, and now it's our job to convert this to logic. So we want to say that something is sorted when something happens. Okay, so let's see if I can boop, boop. We want to use a quantifier like this. Okay, we want to quantify over something to prove that a list is sorted in math. Okay, so let me just show you the answer. It's fun. Here it is. It looks like this. There is a for all. We need that for all. Okay, so here's the idea. Dun, dun, dun. For all I, this is an index. Here's how you would read this. For all I, L of I is less than or equal to L of I plus 1. Okay? So this is like indices, right? 0, 1, 2, 3, and 4. This is what it means for this list L to be sorted. Okay? It's saying that for every index I, you pick whatever you want. You pick 0, you pick 1, you pick 2, you pick 3, you pick 4, whichever one makes sense for this, for the rest of this, because some of them don't make sense. Like, you can't pick I being 4 because there's no I plus 1 in that case. So for every I that makes sense, for every index I that makes sense for L, check and make sure, or I can say it's true that, like the rest of this is true, it's true that L at I L at index I, so maybe you pick 1, you got to pick all of them, it's got to work for all of them, all of the indices that are true, so you got to try like 0 through 3 and make sure that this is true. L of I is less than or equal to L of I plus 1. So it's like, okay, look at this one, pick your I being 0, you have to try them all eventually anyway, and make sure that L of I plus 1, so that's just index 1, is greater than or equal to. Okay, and then you do it for all these pairs. Okay, you have to try all the i's that make sense. So, okay, try this one and make sure that one's bigger. Try this one, make sure that one's bigger or equal to. Make sure that one's bigger or equal to. Okay, so I want to get rid of that. That's the idea. Hopefully that's making sense. For all something, this is true. Okay, for all indices I in the list, this is true, and it means that it's sorted. If this whole thing being true means that the list is sorted. Okay, and I think I essentially said the same thing down here. Yeah. So this is how you would read it. For every I that makes sense for L, L's element at index I is less than or equal to L's element at index I plus 1. Okay, that is all. Not too bad, I hope, but it is a little weird. I will give you that. All right, it is a little weird thinking about this stuff. So let's try again. Let's do this some more. All right. So I don't want to lose this for next time I do this lecture. There it is. Okay. So now let's try a different one. Let's talk about this property. Let's try and write this property using quantifiers. All right. So it's a non-empty list of numbers, always has a minimum. Okay. Okay. That is what we want to specify using logic now a non-empty list of numbers always has a minimum. So like the list 1, it has a minimum. Minimum number is 1. The list 312 has a minimum, and the minimum is 1. So every non-empty list has a minimum that you could pick out. The only one that doesn't is the empty list because it's got nothing inside. Okay? So the very first thing that we need to do when we want to specify this list, this property, is introducing a variable for some arbitrary list of numbers. Okay? We're implicitly saying that like every non-empty list of numbers always has a minimum. You see how I'm translating a to every? That's the key. We have to somehow read that when we read this quote. All right? So we need to introduce a variable for an arbitrary list of numbers, and I guess before I show it to you, I do want you to try it yourself. That's the very important thing to do. Okay? So forget you saw what I just showed you, and try and think of how you might represent this, okay? Just in English for now, but using these kinds of words, like for all, there exists, and, or, not. There's also implication. There's also if-then, right? That's important. So let's think about this, okay? And the one that I came up with is, for all lists L, if L isn't empty, then, so there is an if-then this time, then there exists a minimum value in L. Okay? So you see, we have a for all, and we have a there exists. Isn't that cool? So, yeah, that is the idea. So for all, and a there exists. And our goal, remember, is to translate this into math, and we have to now figure out what to do here. All right? So what does it mean now for there to be a minimum value? Okay? What does it mean for a number to be a minimum of all of the other numbers in like the list of possibilities? So I do want you to think about this one too, and then we'll come back and do it together. So how would you describe the minimum? Like, it's the smallest thing above all the others, right? For every index, it's smaller than or equal to every other thing, right? Because you also have itself that you can compare against. So like, compare everybody against this thing, it's always less than or equal to. That is a good definition of minimum. That's what most textbooks mean, okay? So we're describing the minimum using math, and we're figuring out which properties of a number make it the minimum value. And I'm saying that it's the number is the minimum when, compared with every other number, it's always less than or equal to, okay? Or if you compare it with every number, including itself, it's always less than or equal to still, because it's still the smallest. And it's equal to itself, all right? So it's less than or equal to every other number in the list. So that's how you do it, all right? So let me get rid of all of this, and here's what we want. And here's eventually what it will translate into, okay? So we need some variables, okay? We need some variables to talk about the index, because we had to say for all I. That was where we introduced the index. We have to talk about the indices of the other numbers as well, right? So that's the idea. We need to talk about the minimums index and the indices of the other numbers, and this is the English translation that I will now write out for you. So here is how you can say a non-empty list of numbers always has a minimum, how you say it in math. You say, for every list L, call it L, for every list of numbers, if L's length is greater than or equal to 0, so we can say len of L, because we have that now. If it's greater than or equal to 0, if that's true, then all this other stuff is true, okay? Then, well, there is an index in L. There exists some index called, I don't know, min index or something. There exists that, such that for every other index I, or just every index total, because we can include itself, there exists some index such that for every index I in L, such that all of those, considering all of those, L at the min index, L at the min index, if I could draw an M, is less than or equal to L of I. Okay, so that's essentially what I wrote down here in English. I want you to read it that way, okay? It's like this. So for all lists L, if because implication gives you if and then. If this side is true, then all of this is true. If this part is true, if the length of L is greater than or equal to 0, then we get this. We know this. This should be true. There exists one index, call it the min index, such that for all indices, the L at that min index, the current list that we're talking about, call it L, the L at that index is less than or equal to L of I for every I. Okay? There's a lot going on in this statement. There's a lot to unpack, I know, but I hope that you see it. I hope you see what's going on here. Okay? L at min index is less than or equal to L of I. Okay? That is the idea. Okay? And yeah, it is a bunch of weird stuff. I know these quantifiers, they look weird, and it's weird to unpack all this stuff, but with enough practice, I promise you'll get it. Okay? And this, I think, is where I want to leave you, because you have a longer essay than usual to write, so I'm going to give you some extra time to work on that. Yeah, so we're going to come back, and I've moved this down here too, because it seems more useful there. So we're going to come back and talk about, like, we're going to get more practice of translating from English to these things called predicates, which have quantified variables in them, okay, to code, okay? That is the idea. We're eventually going to get down to code as well. So that'll be next week, and I will now see you in the programming lecture.